Hey everyone, welcome to our video about population growth. What we're going to be talking about here is how populations change size or stay the same size over time. It depends on the number of births, deaths, immigration with an I, and immigration with an E. The two factors that can increase the size of a population is having more births, so more babies means the population's getting bigger, or immigration with an I. Immigration with an I means that some organisms that didn't used to live there are now coming into that population. Things that can have a negative impact on population size or decrease population size are deaths. So, if a bunch of organisms from a certain population are being hunted, that could cause a decrease in that population, or immigration with an E. If a bunch of individuals are moving away or leaving that population, that can cause a decrease in population. There are many different phases of population growth that we can look at on a graph, but you have your initial growth, and then exponential growth is when it grows at a steady rate. And then you have a steady state of that population where it doesn't really increase or decrease in size. And a lot of times, for most species, the population will decline, and that can happen quickly or over a long period of time before the organism eventually goes extinct. Let's first talk about exponential growth. You can see exponential growth here on this graph. It is a kind of a J-shaped graph. And what that means is that individuals in a population are reproducing at a constant rate. So you go from having two rabbits, and they reproduce and they produce, maybe they produce four offspring. And then those four offspring are able to reproduce with each other, and you're going to get 16 offspring from that generation. And they reproduce with each other, and you end up getting 32 in the next population. And they reproduce, and it's like the game 2048, but you end up getting huge numbers of bunny rabbits in that population. That's exponential growth. This can only occur if there is a lot of space and a lot of food for those organisms to live, and if there's protection against predators and disease. So if it's a rabbit population and it's growing exponentially, that can happen if there's plenty of land for them to have burrows, if there's plenty of food for them to eat, like lettuce or grass, if there are not snakes and hawks and foxes to eat them, or if they are not diseased. So exponential growth can happen for a while, but it can't happen forever. But it's one of the big trends that we see in the growth of populations. You can see it here in the growth of this bacteria population. We're kind of at a steady state for a while, but then it starts to grow exponentially at a constant rate until there is a very high population. Now, this one's going to eventually run into the problem that there's not enough space. The elephant population can also grow, so it's not just tiny organisms that can grow exponentially. Some of the very largest organisms on Earth can also grow exponentially. They can exist at a steady rate and then kind of take off and grow exponentially until there is some sort of limiting factor like predators or disease. Most likely, once you've grown exponentially for a while, you're going to reach a carrying capacity when the population's growth stops or slows down. And the model that we use to show that part of population growth, where it slows down or stops after a period of exponential growth, is called logistic growth. Logistic growth is an S-shaped graph, so you can kind of see it looks like an S, but basically there's exponential growth followed by slowing down and kind of reaching its limits or carrying capacity. That basically occurs when there are fewer resources available, or maybe there are more predators, or possibly immigration is occurring. But for whatever reason, that population stops growing exponentially and it maintains a steady state for a long period of time, potentially, and that is at its carrying capacity. This is exponential growth when it just is increasing, increasing, increasing. And this is logistic growth where it has already increased and then it levels off. The part where it levels off is referred to as the carrying capacity. That's pretty much the largest number of individuals that a certain environment can support. So let's say in that bacteria on the petri dish example, you grow, 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 lots and lots of bacteria, but you reach a certain limit because the petri dish is only so big. It can't hold just infinite numbers of bacteria. There's a size limitation. And so once that bacteria reaches its carrying capacity, it might fluctuate a little bit, but it's not going to get too much bigger as a population because there's just not enough space. So it's going to stay at that carrying capacity. This is logistic growth because it started exponentially, but then it leveled off at the mark of carrying capacity. Here's an example of some logistic growth that you can see in a yeast sample. So right now it's at the steady state at the beginning. All right, the yeast is starting to grow exponentially. It's continuing to grow exponentially. We have not reached the carrying capacity. And this bowl is getting pretty full, so this yeast is going to be beginning to reach its carrying capacity. The limiting factor is the size of the container that it is in. There's not enough space for the yeast to continue, increasing in population. So we're reaching our carrying capacity, and that's going to level off and remain about the same size from now on. Thank you so much for listening.